Chapter 14, From Randomness to Probability.
How many figures?
3.
Ooh.
It's an easy one to work ourselves back in with.
That is better
Often
than
they're probably like 13 pairs.
Think about the word from.
I just did
Now I have to.
Oh, I thought you said I did. I was like, no, I didn't.
No, I forgot it.
How dare you?
Bability.
What's that word? Mobility?
Bability. What's the last syllable?
Oh, this is when we get to the fun stuff.
The what?
Get to play past the piggies.
Oh, yay!
Is it with this chapter or next chapter?
You almost. Is that like the least amount of points you can get?
That's
No,
how I made
on his side you get the
That's
least
what happened
amount.
to my phone on the bus. I literally went to take it out of my pocket or something. And
You went
I
to show
grabbed
us
it.
something really fast.
Oh yeah, I went to show it something really fast and I accidentally threw it up.
If the window would have been open, it would have like it bounced off the window and hit your face, right?
Yeah, it bounced off the window, hit me in the head.
Oh.
Oh, fuck.
So mean. I'm not pulling almost threw their phone out the window.
I lost my phone at the fair once.
Alright.
I lost something
once.
Random phenomena. Trial.
Never had that.
Each occasion that we observe random phenomena. I'm not writing that word out a million times. Outcome. The value of the random phenomena during a trial. And the sample space is all possible outcomes. All right, next we have the law of large numbers. And this says that as the number of independent trials increases, the long run relative frequency of repeated events approaches a single value. Now this long run relative frequency, the definition for that, or like explaining what that is the value they approach is the probability of the event So this is kind of like, you know, if you have a coin and you flip it, like what's the probability of you getting heads?
Like 50%.
What about tails?
Also 50%.
Okay, but realistically, if you flip the coin 10 times, are you actually going to get 5 heads and 5 tails?
Or
Not.
More than likely not. But if you flip it 100 times, are you going to get maybe more likely to have 50 heads and 50 tails? Okay, according to the law of large numbers, it would say that basically the more trials we have, the more likely that is to get to the actual percentage of what we would expect to see. So if we flipped it 1,000 times, we should be a lot closer in percentage to a 50-50 split than if you flip it 10 times, basically, or even 2 times, then you should get 1 heads and 1 tails. But we obviously know that that doesn't always happen. When this value is based on repeated observation, it is called empirical probability. Now, a key point, something to make a note of, the so-called quote-unquote law of averages meaning like if let's say you are a 70% free throw shooter and you've
No.
and you've shot like 6 times and you've missed, right? Every time, let's just say. But you should have been making it, okay? Like, so in the game, you've shot 6 times and you've missed. They would say that statistically, you are, quote unquote, due to make one, right? Well, that's not actually a thing. Like, saying that this is due to happen, or like if somebody, is a 30% like hitter in baseball and they've gone up to the plate 3 times and have missed every time, then that 4th time, like, they should hit the ball. That's not actually a real thing. People say that, they're like, well, this hasn't happened, so, or 1 in a million flights crashes and 999,999 have not crashed, so that means if I'm on that millionth flight, mine's gonna crash. Like, that's saying something is due to happen isn't a real thing. So, as crazy as it sounds, people try to say it, so.
Yeah, I mean, I'm due for $1 million, like, eventually, to be given to me, right?
Definitely. Somebody won the Powerball right after midnight the other night for New Year's.
Whoa.
They had like 5 people, and they were like, one of you's gonna win $1 million. I was like, oh, well, I don't know if I like those odds or not. I like them better than mine right now, but
Yeah. I'd be freaked out if I won like Powerball right after midnight.
all your friends would come out of the woodworks.
Yeah.
All right, so the so-called law of averages is saying something is due to hit because it hasn't happened in a while. Is a fallacy.
I like that word.
Now, in this unit, there's going to be quite a few formulas that you're going to need to know, and you're about to get a couple of them now. Empirical probability for any event A. So the probability of A is equal to the number of times A occurs divided by the total number of trials and this can be like a in the long run type thing. So like what ultimately is going to happen. So that doesn't mean like you're rolling the dice and seeing what's actually happening. That means like, what are my odds of rolling a 6 on a 6-sided dice? Like, that's what this is talking about more so. The other one is theoretical probability. Actually, I think I said that backwards. Based on mathematical models not observation. Yeah, I said those backwards. Reverse what I said. The first one is what you actually witness happening. Theoretical is what should happen mathematically. I don't usually think about the name difference. I usually just think about the formula and just do it. So the P of A is equal to the number of outcomes in A divided by the number of possible outcomes So an example of this, the probability of a face card. Now, when I say that, do y'all know what that means?
Yes.
Like
A
king
jack,
or queen?
queen, king.
A jack, a king, or a queen. Okay, so how many face cards are in every deck of cards? Actually, better question. How many cards are in a standard deck of cards?
52.
52. Okay, I'm glad y'all know that. Some years I have classes that have no
Does
idea.
that not count the jokers, or does that count the jokers?
It does not.
Does not count the jokers.
50, 54.
Some classes have no idea when I ask them. Now, I'm just going to ask you this. How many suits are in every deck of cards?
4.
4. Okay. How many of each card or of each suit are there? Like, how many cards are in each suit? 13. Okay. All that is critical information that you know. That's just understood stuff that you should be aware of prior to doing these problems. I had a class one year that had absolutely no idea. I literally had to bring in a deck of cards and show
They
them.
didn't know what a face card was?
They didn't know anything about a deck of cards.
Have they never played?
Like, they didn't know how many cards were in a deck. They didn't know how many suits there were. They didn't know what they were. I was like, okay, we're going to just go back to the basics here.
I'm just curious as to
I wanna
what
play
the guess
War.
was for like the number of cards.
I don't even remember.
Was it that bad?
But they had no idea how many. I mean, it was just,
That sounds rough.
I like literally had to write them out for it. It was, yeah. So anyway, so how many total face cards are there in a deck of cards then? 12. So this would be 12 possible face cards. So the number of outcomes in A. Out of the total number of possible outcomes, which is 52. So 12 out of 52, which we could reduce down to 3 over 13. You could also get a decimal, but that's sufficient. A lot of times we'll leave things in fraction form for this. It just depends on what it's asking us to do with the information, because sometimes we're asked to use this information for something else later on. It's like the mystery mouse tool. It's a tool we can use later. It's like that. You never know. Anyways. So this is the number of face cards over the total number of cards in the deck. All right, now, just something to remember. Random events are not equally likely. All right, so now we're going to get into formal probability. Now, keys with this are going to be draw it, Venn diagrams, and one more, but I'm going to tell you something else before I give it to you. All right, the first thing is probability is a number between 0 and 1. It is not a percent. It is a decimal. So for event A, 0 is less than or equal to the probability of A is less than or equal to 1. If the probability of A is equal to 0, then the event can't occur. If the probability of A is equal to 1, then it always occurs. Now, it's very rarely a probability of 0 or a probability of 1. Not that it can't happen, but typically it's going to be some other number, unless it's like the probability of rolling a 7 on a 6-sided dice, like, obviously.
It's a hard one.
All right, the second thing, the set of all possible outcomes of a trial must have a probability of 1. Now, I'm going to leave a little bit of space over here to draw something. So just like, I would say leave a tiny bit of space over here. So the probability of the set should be equal to 1 is how we would write that. If A is the event, then A, and then like in the exponent, there's a little c, that means the complement of A. And is all events not in A. So if I said we had the numbers 1 through 10, and I told you that A was all the odd numbers, the complement of A would be all the even numbers. Okay, they're in the set as a whole, but they're not in that individual set that I'm breaking down for you.
So would you say, so you wouldn't say that it's the opposite per se?
No, it's everything not in. Yeah.
Just in that specific situation.
Right, and that could change based on what your set is. So like there's a downside to the way that we do this class, because when I took it, we took a class that was called finite math, where pretty much all we did was set stuff. So we learned a lot about that kind of stuff. So when we got to stats and we were doing probability, because our class was actually called like prob and stats, so like we did anyways, but it made it understandable a little bit better. College algebra, I actually teach this. There's actually like a whole section on this, so you teach it in there. But anyways, you get like the quick rundown basically. So this whole thing is the set. Sometimes we call it the universal set, but it's just the set as a whole with all possible values basically. Then within there, we have the set A, or the event A. And then we have A complement is everything out here that's part of the set but isn't in the actual event itself. Now, you said something about, well, it's not really the opposite, and it's not. So I'm going to tell you what the complement rule actually is so that you could mathematically figure that out, because obviously me telling you that, if you have the set of 1 through 10 and I said A is odd numbers, it makes sense that the complement is the even numbers. But when you have different values and stuff actually put in there that you don't necessarily know that kind of information, since this is formal probability, you probably would like to know how to find the complement in that situation. So the complement rule says that the probability of A is equal to 1 minus the probability of the complement of A. And the reverse is true, that 1 minus the probability of A is equal to the complement of A. So that also. All right, this next part is where people tend to start to get confused, okay, just because of the wording of things. So 4 is going to be the addition rule. Now, this is going to be a general addition rule in another section, or possibly in this one later on. I think it's in the next section. We have an addition rule for something that's more specific. So it's going to look different. So there's going to be one that's going to be your general addition rule, and then there's going to be like the actual addition rule. So I'm just prepping you for. You won't get confused right now probably, but when you learn the next one, you're probably going to be like, well, how do I keep them apart? So anyways.
So is this the general one?
General. Yeah, I think so. I don't know. I'll tell you. I'll give you a whole sheet of formulas before the quiz. I don't want to say it is and it's not, because I don't remember off the top of my head exactly what it is, but basically yes. Anyways, if events A and B are disjoint, then the probability that one or the other occurs is the sum of their individual probabilities. So I'm going to give you a little visual of what this looks like before I give you the rule. So I'm going to have event A and I'm going to have event B. So in this case, with them being disjoint, what that means is they are mutually exclusive. They have no outcomes in common. Okay, so there's no overlap. So when we get to the other rule that I'm telling you about or that I mentioned, there's going to be overlap. So this rule is the probability of A or B is equal to the probability of A plus the probability of B. Now, the other way that or sometimes gets written is the probability of A union B, which you've seen before when we've done domain and, all that fun stuff. But that means or, okay, so that's a notation thing. And this is still, probability of A plus probability of B. So either way, sometimes you'll see it written A or B, sometimes you'll see it A union B.
So.
And U is just union or.
So when you say A or B, what exactly do you mean
So
by
it's
that?
saying basically A or B is everything in A plus everything in B.
Right.
What you're gonna see in the next section or whenever it comes up is that when there's an overlap, we would be counting that value twice. So what we're gonna do is we're gonna have the probability of A plus the probability of B minus the probability of the intersection of A and B. That's why I said I don't remember which one is officially labeled as general and which one's labeled as specific because it could go either way. You can always use the one where you minus something off. In this case, you'd be minusing off 0
Okay.
because there's nothing overlap. So if there's an overlap, we have to remove the overlap because otherwise it gets counted twice. Just a thing here. Events are disjoint or also called mutually exclusive if they have no outcomes in common. So in this situation here, we would say that A and B are disjoint if we were talking about just the two sets individually. All right, so that's the addition rule. Next, we're going to have a multiplication rule. Which says for two independent events, A and B, the probability that both A and B occur is the product of their individual probabilities. So in general, when we're looking at this, or like when we're trying to figure out the multiplication stuff or whatever, we're going to have basically two events here that are occurring. So still A and B. Now, if they're independent, there's technically no overlap. But just for the sake of you seeing this, how I normally draw this. This middle area is A intersect B. So, again, this is provided that these are independent. And eventually we'll have a formula for proving that things are independent. But right now we're just take my word for it, basically. Okay. So the probability of A and B is equal to the probability of A times the probability of B. The other way we can write this is the probability of A intersect B, which is just the union flipped upside down.
Why do we have to flip that upside down? Oh, because it's not or.
Because it's an intersection. It's an and.
That's funny.
Like I was saying, it's much money.
Now, y'all have the benefit of you've done a lot with unions because of doing domains and asymptotes and all those things. So you've unioned a lot of things in your time. Some years when people haven't done that, they're like, how do I keep the difference? And I'm like, well, union is a U, and it means or. And I'm like, intersection is like an N, like an intersection.
Yeah,
And it's
they
like
can go over the
and,
bump.
like there's an N in the middle of and.
Like you can go over the bump because it's and, but you can't go in like the dip because it's or. You have to choose. You can't go both. You know what I mean?
You can go uphill, but
No.
you can't.
Whatever works for y'all.
Confused me more.
Really?
I don't.
No, it didn't.
How do you know it didn't?
You're
You're not.
mean.
You're not in my mind.
You're just being mean.
I'm literally not.
Yes, you are.
Confuse me more.
I want you.
Who are you gonna
I
tell?
want to tell my mommy.
What your mommy gonna do?
I don't know.
Nothing.
Okay.
You call your mommy.
Many statistics methods require an independence assumption always consider if independence is reasonable before using the multiplication rule. And like I said, eventually we'll actually have a way to check, but overall we're going to assume independence for this section. All right, I'm going to set up an example, but I don't think we're going to have time to get through it, so I'm probably just going to like set it up and then we can just go in and like fill it in tomorrow. So given the probability of getting a green, red, or yellow light at a particular intersection is, so the probability of green is 0.35. The probability of yellow might be kind of hard to see, but probability of yellow is 0.04. And the probability of red is 0.61. Now you're probably like, how in the world do you get a yellow light? Like, obviously it's going to either be green or it's going to be red. Like, it's not just going to be yellow. But it means, like, as you're pulling up to it, what's happening is what it's asking. Like, you don't have to read into it too much.
Okay. I was thinking that. I was like, it doesn't really like.
It won't just, like, stay yellow.
Yeah.
It's like the yellow flashing arrow when you get to, like, some of those, like, the intersections that have, like, you know, y'all know what I'm talking about.
Yeah. I know.
Sometimes they stay yellow for quite a while.
Yeah.
Yeah.
So,
Those two, yeah.
the first question is going to be, what is the probability you get a red light on 2 consecutive days Now, I have like 2 lines of work, so if you want to skip like 2 or 3 just to make sure you have enough. Now, I went side to side with my work. If you prefer to stack it, then add 2 more lines than that, probably. What is the probability you don't see a red light until the 3rd day? Just because this one's subject to how many lines you could need, we're going to stop there, but there's going to be one more question that comes after that. So I don't want to make you skip a bunch of lines and then you don't actually need to, or not skip enough and then be like trying to cram it in. But anyways, there's only one more question after that, but that also takes up a decent amount of lines, so that way you'll have it all together. But